The question over here is to reverse a singly linked list, and the solution has been explained after evolution and has been clearly elucidated as well. You can also find the running program at the link mentioned over here. Now, in the current content, we are going to explore the three-pointer method. This is the most efficient method to reverse a singly linked list. There are other methods, and in fact, the other method is the stack method using recursion, but that is expensive because of the huge amount of call stack involved. However, the three-pointer method in comparison is a lightweight and efficient and a quicker method, and that's the reason why we are looking into the same. Now, what exactly do we need to do here to reverse a list? For the sake of simplicity, I have taken a simple example with only 3 nodes. However, the same would be true or applicable even for a huge number of nodes. Now, if the list contains elements 1, 2, and 3, and if we want to reverse the list when printed in reverse order should give us 3 to 1. That is what is the expectation. The current head is at 1 and 3 is null terminated. On reversal, the head should be at 3 and 1 should be null terminated. To achieve this, we have to start from 1. We cannot start from 3 because to reach 3 we have to do a huge amount of work, and that gets us into a tricky situation because we have to first locate 3 by moving completely from left to right, and once we reach 3 we have no way of getting back to 1, and it gets very complex and tricky. That's why what we prefer to do in this case is we start from 1 and we null terminate 1 to begin with, and we move from left to right, and in every iteration from left to right we go ahead and fix up the link by reversing the direction of the link. So after fixing up 1, what we do is we move ahead and fix up this link between 1 and 2. Instead of the link pointing from 1 to 2, we will make it point from 2 to 1, and going forward we will make the link point from 3 to 2, and we will stop this iteration once we hit the null terminator. To do this, we will need 3 pointers. The reason being, the first pointer is required to null terminate 1. The head of the node is 1 in fact in this case. The second pointer is the current pointer or the head of the node, and the next pointer is the one on the right hand side of the head of the node. Now, when we move all these 3 pointers in every iteration, we will get to a point when the next pointer hits null or gets null terminated, and since the current pointer lags the next pointer by a link of 1, the current pointer will be at the head position. When the null pointer or the next pointer is at null, the current pointer will be at the head position, and that would be the head of the list. This is exactly what we will keep in mind during algorithm design and development. Now that we have fixed the first link in the traversal, we see the side effect. The side effect is that the link between 1 and 2 is broken, but that's not a problem. We will be able to fix it in the next iteration. However, to complete the current iteration, we have to move all the 3 pointers by 1. We have to phase shift them by 1. So previous pointer which was pointing to null now will point to 1. Current pointer which was originally pointing to 1 will now point to 2, and the next pointer which was pointing to 2 will now point to 3. And this has been captured in the set of operations over here on the right hand side. Current pointer arrow next is equal to the previous pointer, and previous pointer becomes equal to the current pointer as we said, right? So the previous pointer which was here now assumes the position of this current pointer and hence comes here. The current pointer assumes the position of the next pointer. So the current pointer which was over here assumes the position of the next pointer, and hence the current pointer comes here. The next pointer further right shifts and goes from 2 to 3. That is what happens here. and this completes the first iteration. In the second iteration, what we will do is we will fix up the broken link between 2 and 1 by pointing the current pointer's next link to the previous pointer. This is what we will fix, and again we right shift each of the pointers. So the previous pointer will now move from node 1 and will point to node 2. The current pointer will move from node 2 and will point to node 3, and the next pointer will further right shift and will hit the null terminator. And this is exactly where we land up once the set of operations over here is executed. Next pointer will now be null terminated, and this means we have hit the end of the list. Now that we know that we have hit the end of the list, we still need to do one fix up over here between 3 and 2, and that fix up is done by the solitary operation here. Current pointer arrow next is equal to pptr, or cptr arrow next is equal to pptr. Once that is done, this link is complete and the head of the list is at 3, or the current pointer is at 3, and that is the new head of the list. This is how the 3-pointer method works in brief. If we have a look at the building blocks of this algorithm, we essentially see that there are 3 building blocks. The first is initialize, the second is iterate, and the last is the fix up of the link outside the iteration or post iteration. When we look at the first block, initialize, closely, we see that we initialize the 3 pointers, and that is the initialization step where previous pointer is null, current pointer is set to head, and the next pointer is set to the element next to head. With respect to iteration, as mentioned earlier, we have to fix up the length, or rather we have to fix up the link over here. And once the link is actually fixed up, we have to move each pointer to the right, and we have done that over here in these 3 steps. Previous pointer is equal to current pointer is equal to next pointer is equal to next pointer arrow next, right? And if we see these 2 figures or these 2 rows very carefully or closely, we see that these operations are identical. The first operation, or cptr arrow next is equal to pptr, will fix up the link, and the other 3 operations, as mentioned earlier, will ensure that the pointers are moved to the right by 1 position, and that explains the iteration block. Likewise, outside the iteration block, or once the iteration is completed, we are still left with 1 fix up over here which needs to be done, and that has been taken care of by this operation over here. cptr arrow next is equal to pptr, and that concludes the building blocks of the algorithm. Now we construct the pseudocode from the basic operations. Well, in the basic operations, or the basic building blocks, we initialized the 3 pointers, and then we did an iteration where the first step was to fix up the link between the current pointer and the previous pointer, and the next step was to move all the pointers to the right, and again outside the loop we had to fix up the solitary link that existed. This summarizes the pseudocode, and now we will see how to translate the pseudocode into code. With respect to pseudocode to code translation, we look at step 1, that is initializing the 3 pointers, and that's exactly what we do over here. And the step number 2 is that of iteration, where we check the termination condition of whether the next pointer has hit null or not. If next pointer is not null, we continue the iteration, and if it is null, it means we have hit the termination condition for the loop. And as part of the iteration, we do 2 things. One is we fix up the link which we do here in this solitary operation. Current pointer arrow next is equal to PPTR, and in the next step we move all the 3 pointers, and each of the 3 pointers is moved over here on each of these 3 lines respectively. Once the loop is done, the solitary link that exists outside the loop has to be fixed up, and that is done here as well. This completes the pseudocode to code translation. As part of code development, all that I have done here is added the function signature by mentioning the function name, the return type, that is node star or a pointer to the node, and have defined the input parameter as well as a pointer to the node. Further, I have also assigned the head to the new pointer so that the head now points to the new pointer, and have returned the head value. The rest of it remains absolutely the same. Exception handling has been incorporated to make the code robust. So the only check that we have added is to check whether the list exists, and this is done by checking whether the head is present or not. If the head is present, or if the head is not a null node, we go ahead and do exactly the same work as before, and if the head is null, we just return the null value which we have obtained from outside the if condition. If we don't do this, the program is going to crash over here when we try to find a CPTR arrow next. Hence the need for exception handling. This function is going to work fine for all use cases, including no node as the head of the list, one node as the head of the list, 2 nodes, 3 nodes, and n nodes as well. Let's talk about the algorithmic complexity. There are 2 complexities here. One is the time complexity and the other is the space complexity. With respect to the time complexity, we focus more on how quickly the algorithm scales with data. And in that context, we see that there is a while loop which will execute n times if there are n nodes, and hence the complexity is O of n, where the atomic operation or the basic operation, if I may say so, is to reverse the link. That is the basic operation, and we see that the complexity is O of n for time. Also, if we look at space complexity, we need n nodes to hold the input size, and we also need 3 extra pointers over here to do the extra work associated with the algorithm. So typically we need n plus 3 nodes in all, and in that context the space complexity includes the input complexity and the auxiliary complexity, which is O of n plus 3, and if we approximate that, we again get the space complexity as O of n. What I have done here is I have now created a list over here based on the 3 arguments in the command line argument text box here, and once the list is created, I have printed out the list starting from the head, which means we will get 1, 2 and 3. Then I have reversed the list and I get the new head of the list, and I print the list again with the new head. So the first printf is going to give me 1, 2 and 3, and the next print is going to give me 3, 2 and 1. The algorithm for reversing the list, which is the core algorithm, is the same as what was there in the presentation, and that's what has been captured over here exactly as is. Now let's run the program and see how things work. So I run the program, it compiles and it runs, and the list is as expected, it is reversed. You are welcome to run this program at online GDB. The link has been provided as part of the presentation. If you have any questions, please feel free to reach out to me. Let me know your thoughts or share your comments. And if you found this video useful, please do like it. Thank you so much. Talk to you later.